All right, let's talk about these limits. These are generally pretty good for you guys. You're getting the idea of how to evaluate them graphically. And just remember, evaluating a limit, it's about approaching an x value that you don't actually get to. You get infinitely close to it without actually touching it. So where that plays out is, for instance, this first limit in part A is the limit as x approaches 1. There's no plus or minus next to that 1 in the upper right-hand corner. Therefore, it means the general limit from both sides, from both the left and the right. So I put 2 red arrows there indicating as we approach x equals 1 from both sides, since there's no indicated direction, you consider both. And if they agree, they go to the same height, then you write that value in, which is 2. And then the second one is actually plugging in a point. So this is not a limit, this is just putting -2 into the function and saying what's the value, and it's -1. And then finally, on that first row, is the limit as x approaches -2 from the right. So I have an indication of an arrow coming in from the right toward that x value, and we're heading to a height of -1 again. And then D, as x approaches 2 in general, that's from both sides. If you see those green arrows over on the right, they both approach the same height of 1. And then as you put in -4, this isn't a limit, again in part E. If you put in -4 directly, the height -2 is what you get. It's actually a point on that lower curve just below -4. And then as you approach 1 from the left and the right, those are the pieces of that general limit we did in part A, so I just put them back in there, but both of them go toward 2, which is why that first question, part A, the limit as x approaches 1 in general, is also 2, because the two one-sided limits agreed. And then finally, H is plugging in -5 into the function. If you go to -5 and look at the function as a whole there, and there's no other point, no other solid dot to replace it anywhere else, so it does not exist. And f of 1 is 4. That limit we were always approaching 2. As x approaches 1, the limit was 2 because we were approaching that hole without getting there. But once you go exactly to x equals 1, you land on a solid dot at the height of 4. Okay, next piece is the derivative stuff, and I know a few of you are still struggling to kind of pull together what the formula is, how to use it. But f of x plus h and f of x are the components of that. The idea is we're taking a secant line and shrinking it down infinitely small and using that to get the tangent line. So the derivative is a formula that gives you the slope of the tangent line anywhere on the curve f of x. So with this formula, there's f of x plus h. I just wrote it in purple there. That's in purple. I indicated the two parts of the formula are the f of x plus h and f of x. I put them in purple and yellow to make them stand out for you, how you write those. Some of you still not quite sure how to write f of x plus h. It's just substituting x plus h in for the x's in your f of x function. And then you subtract those two with some algebra, but first the f of x plus h requires some work, some foiling out the x plus h times x plus h, and distributing the -5 and all that good stuff. And then don't forget, it's always a limit as h goes to 0, right up to the end. So when you get to the very end, the key piece that you're looking for is with the algebra on top, you will be able to simplify it way down. And so the simplified stuff, I'll highlight here maybe in some yellow or something, but there is a simplified chunk here. This is what the numerator ends up simplifying down to. Well, not quite that. It simplifies to what's right above here and ends up starring. And then after everything cancels, what's left all has an h that you can factor out. And so each term in what's left has an h that can be factored out. And so that expression below, factor out the h in the numerator, there's an h already in the denominator, those cancel. That's the moment of when we can finally finish and evaluate this and find the derivative, because once the h in the denominator cancels, we can put 0 in for any remaining h's, because a limit as h goes to 0, you can always try and plug that value that h is approaching, or if it's a limit as x approaches something, direct substitution of that value is great, but a lot of times we can't do it because it causes division by 0. But after canceling, then you can put that value in directly. So that's what's being shown there. The very last step, 0 is being plugged in for the remaining h's, and you end up with 4x minus 5 is all that's left. That's your formula, the derivative, which tells us the slope of the tangent at any x. And then I also asked, hey, why don't you just tell me the slope of the tangent at -3? And that's by plugging -3 into the derivative function, and the slope would be -17. Okay, next one. Same process, even if it's g, you're doing the g of x plus h function minus the g of x function, and this one requires a little foiling out, so here's the long foiling out, x plus h times x plus h times x plus h. And then once you simplify all that, and then minus 3x cubed, there's some things that cancel. They're denoted there by being crossed out, and then what's left has the remaining terms at the stage right here that I'm starring. They all have an h that you can factor out, and then once you factor out that h, you cancel it, and then you can put 0 in directly for all the remaining h's, leaving just 9x squared behind. And then I ask for, hey, what's the slope of the tangent at specifically x equals 2? So you put 2 in for the x, and you get 36. Okay, the left rem, right rem is approximating area under a curve, and definitely not exact. And we want to just get, and left rem means you want left rectangles of a set amount. We're going to do 5 of them in this problem. And right rectangles means you're going to do right rectangles that touch on their right edge in the interval described, and we're going to do 5 of them as well. So the interval is 0 to 5, so you kind of cordon that off, and you just say we're only putting rectangles, 5 rectangles from 0 to 5. And since there's 5 rectangles in a width of an interval that's 5 long, they're gonna be 1 wide each. So we call it delta x, the width of the rectangle. 5 minus 0, that's the width of the interval. And then number of rectangles is 5, and if you divide those two, you get a width of 1. And that's really important. Now we've been factoring it out. Really, it's just every rectangle has a width of 1, but a unique height. And instead of just taking them times 1, times 1, times 1 for each of these rectangles, we just put a factored out 1 on the outside, which means all of those would get multiplied by 1 each rectangle. So left rem, the very first one that you see up on top, the first height of the first rectangle is 4, and I've got it marked in purple over on the left. You can look at the graph, but ultimately you want to get to the place where you can get the height of that left rectangle if you just know that the left edge of that first rectangle is going to be touching at the lower bound of our interval. Our interval is from 0 to 5, and because it's touching left edge, that's from plugging in 0 into the function f of x. And then, so that's f of 0 gives us 4. So if you plug it in there, 0 squared plus 4 is 4. The other points are all the same thing. The other heights are, the last rectangle I've denoted in there is f of 4 is the height of it, because the interval goes to 5, but if you're doing 5 left-touching rectangles, the very last rectangle's left edge would be above x equals 4, and that's the height that we need, how tall it is. So you plug in 4 into the function and square it and add 4 to it, and you get 20. So with left rectangles, you do the lower bound as your first input all the way up to 1 rectangle width less than the upper bound for the last one. And then right rem, it starts kind of, it's the converse of that, because the right edge of the very first rectangle touches at not the lower bound 0, but at 1 width of a rectangle over from that. So it actually starts at f of 1 versus, and then the last rectangle's height is the very last part of the interval of 5. F of 5 will give you that height of 29 because it's all slid to the right hand side. And each of those is 1 unit wide. If I said, hey, do 10 rectangles, then each, you'd have to take each rectangle times a half, and I would have put a 1/2 outside of the sum of all these heights instead of the 1. So my delta x would be half if I said, please do 10 rectangles on this interval. And it also means you'd have to put in a lot more heights. You'd have 10 different heights to calculate, but it would just be, f of 0, f of 0.5, but you can look back at your past practice exam and some other problems that we did in the past to deal with that. But that's the story on those, and these are correct values. Just check them against yours, email with questions, and I'll see you very soon.